Hello everyone and welcome. My name is Eric Coleman with IISD and I will be the moderator for today's webinar, When Agile is a Quality Game Changer, Predictive Forecasting for Defect Profiles by Michael Ma. We're excited you're able to join us today. Set aside an hour to attend this webinar. This webinar is one of a series of free webinars to introduce the topics as well as the presenters of the upcoming PSQT conference in San Diego, California, August 14th through the 19th at the Sheraton San Diego Hotel and Marina. PSQT is the only conference that focuses on practical best practices in every aspect of software quality assurance and testing. The ongoing theme of the conference, Practical, Proven, Feasible, keeps the focus on what works. To learn more about this exciting conference, visit psqtconference.com. You may submit your questions at any time by using your question box in your GoToWebinar window. Today's presenter will answer as many questions within the time allowed at the end of today's session. This webinar is also being recorded and will be made available for viewing within 48 hours at psqtconference.com. At the end of today's webinar, you'll be asked to complete a short survey. At IISD, we strive to provide the highest quality educational resources for the public and would appreciate it if you could take a few minutes to complete this short survey. I will now turn the webinar over to today's presenter, Michael Ma. Michael?
Thank you very much, Eric. And welcome everyone. I'm looking forward to today's session. It's a very exciting topic that's going to dovetail very nicely with the upcoming tutorial that I'll also be teaching at the PSQT conference, as well as feeding into the topic that is my keynote speech on Wednesday afternoon when we're out in San Diego together. So let's go ahead and get started, and I'll tell you a little bit about this particular webinar today. It's actually a past keynote speech at a number of quality conferences, so it's one of those high caliber talks that's all about storytelling. And I am not kidding when I talk about this idea about what we're seeing as Agile being a game changer, particularly from a standpoint of quality and clean code. This talk comes from a decade or more of research where a large database of completed software projects has been gathered and collected and analyzed by our firm, QSM, or Quantitative Software Management. A little bit of background about myself is I'm a quantitative analyst, kind of like by DNA. My father was a Wall Street trader when it was an honorable profession. But being someone who grew up with the Apollo space program and the whole passion of NASA and aerospace, I decided to go into physics and engineering, which then led me into quantitative analysis of how engineering projects behave, now specifically software projects. What I'm going to be doing is sharing you some case studies today that really illustrate patterns that are being seen from a data perspective, and really putting some numbers onto what I call a fact-based conversation. There's a lot of hype around different techniques and emergent technologies around Agile, but with that being said, the hype is quite real in that it single-handedly, as a game changer, really reinvigorated the software engineering industry in the United States, particularly if we think back in the 90s when there was a big rush to offshore and outsource a lot of application development, resulting in a huge shifting of labor and economies where places like India single-handedly wound up capturing a large market share of the software economy. Agile has really brought a lot of that back to the United States with the promise of building clean code. So for a quality conference, this couldn't be a more vital and critical topic. So I whimsically say that this webinar is going to touch on the answer to life, the universe, and everything. Not really a little too much overselling, but it's significant from a standpoint of many major trends that are going on in our industry. I'll also preface by saying that what I'm about to share with you has also been the subject of many conferences throughout the United States, North America, Canada, South America, Central America, and Europe. Some of the patterns that we're going to be talking about today are extremely significant for organizations that have software as a critical part of their strategic mission. So let's go ahead and get started and talk about where this kind of began. I mentioned that in my early career I was focused on electrical engineering and physics, and shortly after graduating from Tufts University I wound up having the privilege of being the QA and group lead for the Trident II nuclear submarine program, specifically building the code for the navigation system that flew this ship that's 2 football fields long under the ocean around undersea canyons and mountains with as clean code as possible, because you can imagine that if there's a bug on a nuclear submarine navigation system, a crash would be catastrophic on more than many levels, possibly creating international incidents. So I'm going to tell a little bit about how back then, before Agile even existed, we did a couple of interesting things as we were building this code. First, we co-located all of the smartest people that we could get in one room, one huge room where a lot of the engineering occurred. Second, we had people working in pairs. So not only were the programmers working in teams of 2, but the requirements analysts worked in teams of 2. And third, we wrote tests before we wrote code, and that was my job. I had to actually translate the operational mission requirements of this nuclear submarine into software stories, requirements, before we wrote code. Now, if that sounds like Agile to you, I'd say we were Agile before Agile was cool. And from that, I can tell you that the prime directive was really to reduce bugs. Like I said, if you're driving a $2 billion vessel, 2 football fields long, 24 armed nuclear missiles on board, you better not crash that boat. And so what we were trying to do is shrink something called a defect curve, specifically a Rayleigh defect curve, which is simply a mathematical term for a build-up to a peak and a long tail. At the end of that tail, you will have found and fixed the bugs that were in the code and be ready to deploy this system into the field. Some of you may have questions about defect curves. It's a common question about what are the factors that drive the curves to be higher in magnitude and longer in duration. What are the factors that shrink it? And I'll talk to that. And speaking of questions, I'm going to aim to have plenty of time for Q&A at the end. And while we're not going to be doing it interactively with questions while the talk is going, jot down some of your thoughts, questions, or comments on a little slip of paper so that you can share them with us at the end, and we'll be sure to try to touch on as many as we can. So back to this Rayleigh defect curve. The idea about building clean code could come from a couple of angles. One, you could say we want to have the best QA and the best testing as possible to find and fix bugs in the code and have a highly reliable system when we go live. Or you can say we want to build a system from the start that's as bug-free as possible so that we're not dealing with a tsunami of bugs during QA and test that could overload our test staff. Or you could say, you know what, the combination of the two is the best of all worlds. So if we can build code extremely clean, and then in the pipeline during QA and test, we already have code as clean as possible, and so that the residual work for us to find and fix the bugs in that code curve is as low as possible, then that gives us the best opportunity to, number one, make our date, and number two, have the most reliable system possible. Because no matter what, there's going to also be leakage where some bugs will be missed, and they might wind up crossing that boundary and being put into production even though you thought maybe you covered all the testing. And the fact of the matter is, typically, we don't find 100% of the bugs. We find 90 to 95% of the bugs, and the 10% residual could show up to bite us later on. And I would argue that 10% of a small number of bugs in the first place in code is a better situation than 10% of bugs that could be 4 times more because the code wasn't clean in the first place. So the idea is to shrink this Rayleigh curve as much as we can. And so before Agile was cool, we were employing various practices that today we might call pair programming, we might call test-driven development, we might call co-located teams as a way of driving an Agile-like practice into creating clean code. So what that also brings for me to share with you is that whether you feel that you're really in an Agile state or not, regardless of that, there are still practices that you fundamentally can focus on that are intended to drive code to be as clean as possible. So when we had this really clean code navigation system, this is what it would look like with a submarine underway. Again, the Trident II nuclear submarine was probably one of the most game-changing weapon systems around that was really about preventing any possibility of a repeat of global conflict like World War II. The very idea that this system existed was intended to be a peacekeeping idea because of the significance of exactly what it could do. Basically, a nuclear submarine is like a Klingon warship with a cloaking device, and that cloaking device is the ocean. So, turned out that during the Cold War days, both the United States and the Soviet Union had these super machines that could literally park a few miles from your front door, and with something at point blank range, nobody would ever initiate any kind of conflict. That was the theory of strategic nuclear deterrence, and it felt like it was one of the most important jobs in the world and one of the most important software projects in the world. So this is kind of like Captain Kirk and Sulu and Chekhov at the helm, and all of the software that drove the ship was what drove the Navigation Control Console, or the NCC, which you see right there. Throughout some of today's webinar, I'm going to talk about a different perspective about navigating, because instead of driving nuclear submarines, I drive or fly Piper aircraft. This is a 1946 Piper Cub, and the thing that's different about this is it has no software, just magnetos and vacuum pumps to provide the instruments so that we can fly around the Berkshire Mountains of western Massachusetts. I whimsically throw this in not just to show my young buddy Joe on the left and me in the Piper Cub, but I'll be talking about metaphors about navigation in aircraft as a context of a story about navigating a software project. Okay, so let's talk a little bit about the case studies that we're going to be getting into here today. First, we're going to be referencing something called the QSM Software Lifecycle Management Database, and the basis for the case study today comes from our research of projects that wind up in this SLIM database. Right now, about 12,000 completed software projects throughout the world. What we do in our firm is we actually take productivity patterns, defect patterns, staffing, schedule patterns for projects, whether they're waterfall, agile, outsourced, or in-house, onto the desktop of our client community so that they can gain access to the intelligence behind these software projects. And we've also built databases and models that allow organizations to do their own analytics. So what I'm going to share with you is some of the analytics of a particular series of case studies focusing on Agile and defect patterns from the QSM SLIM research. The database has got the who's who of industries represented in it. This is just a partial list. The common denominator, whether we're talking about an aerospace firm, a wireless communications firm, or a bank, is that software today in the technology era is strategic. It's vital to people's business, companies' competitiveness, and their market share and growth. And regardless of where you are, we're probably looking at trying to identify the best possible way to build code, and Agile's right at the front of that line. So the first case study, or the case study that I'm going to use to share with you about what defect patterns reveal themselves to be, is a company that gave us permission to use them as a storyteller. Follett Software. Basically, they're the Amazon.com of the educational software industry, providing educational classroom materials, digital books for kindergarten through 12th, as well as higher education and college universities. If you have kids in school, they're probably ordering their college textbooks through Follett. It's one of the leading market share providers of educational materials, and I've had the privilege of working with this company going back over 10 years. And so I've got some rich amounts of insights and stories about their Agile, particularly when it comes to the whole dimensions of their strategic competitiveness in the marketplace, and also how they achieved what they achieved. So let's talk a little bit about this particular case study, and their passion is about igniting the flame of knowledge. So they decided to go with an XP approach, following a lot of the ideas of Kent Beck. Kent Beck, by the way, was one of the Agile consultants with the think tank known as the Cutter Consortium, which is based in Boston, where I serve as the benchmark practice director. So where we had an Agile practice where people like Kent, other signatories of the Agile Manifesto like Jim Highsmith, would help companies with an Agile transformation, our benchmarking group also helped measure. So transform into Agile, simultaneously measure, talk to the executives about the metrics that we're seeing. So their idea here was pair programmers working with a customer proxy, the smallest molecule being a group of 3, identifying stories and features that would go into the backlog that would go into a particular sprint or iteration. They were all about co-located into one large room, and 10-15 years ago when they started this endeavor, Brian Smith on the left, who is still working with me on Agile at Follett, would talk about so much damn noise, particularly since his workstation was right in front of the ping pong table. So they went through a lot of growing pains about how do you create a co-located environment that would be optimal to thinking as well as communicating, and building code in teams of 2, in pairs, like this photo. So a couple things that come out from this when we were talking about pair programming from a quality perspective. Other mentors and leading writers like Tim Lister would talk about pair programming as well, and one of the pushbacks against pair programming used to be, why have 2 people build code when you can have 1 and double your cost? So what's the idea behind this? Is that we actually reduce our cost. It seems counterintuitive, because a pair of people working on a block of code is like a pilot and a co-pilot in an aircraft that are constantly watching the code as it's being built, constantly providing instant reviews of the design and the execution of the design into the code by another pair of eyes. Always dealing with the fact that when one person's fresh, let that person take the controls of the plane and let the observer monitor the radios or keep a look over the shoulder and watch what's going on and making any corrections instantaneously. And then switching when one person might get a little exhausted in terms of fresh ideas and another person says, hey, give me the plane, give me the code, let me go ahead and run with this and tell me what you think. And it turned out that this was a style of building code that dramatically reduced the bugs at Follett, and I'll tell you by how much in a minute. Another thing you might find interesting from this screen is something that I saw. I saw people having photographs right under their screen. And I said to the director of software engineering, what's the deal with everyone having photos of their families right under their screen? And they said, well, you know, we take the XP principles very seriously, and one of the things about Kent Beck's values in XP is to work a 40-hour work week. So whereas in the past we were exhausted from working lots of overtime, we now tell people, go home to your children, put a picture under your screen to remind you to not stay too late in the office. If we're in the business of igniting the flames of knowledge, go home and help your kids do their homework. Be with them at dinner. As a culture, Follett was named after the original founding family, the Follett family, and so they took it very seriously that they have a family-driven culture. So this was an interesting thing that I saw in terms of the people aspects of Agile, the management aspects of Agile, aside from the technical aspects of Agile. And that was quite impressive because it worked its way into clean code. The idea being that a tired mind is not a creative or productive mind, and a fresh and a energized mind that's not overworked is a creative and sharp mind in this work that we call knowledge work, which is what software engineering is. So let's talk about a piece of this knowledge work. This is a sketch with my scribbly handwriting that shows a diagram of how a project was staffed, when it started, when it finished, and I'll walk you through this to talk about the metrics on time, effort, backlog, size, and quality that we capture and drive into the SLIM model and do some analytics. So as you can see in the timeline, there's a blue rectangle that represents a pair of analysts, project lead and a customer proxy, working on the story writing. So I sketched out the story writing phase beginning in mid-December, going for 2 people through January, February, March, April, May. As you can see, this is over 10 years ago. This is in 2004. And I'll share with you what we're seeing right now in 2016 with this organization. But way back, even in 2004, we were capturing metrics and looking at defects in this particular first set of data on Follett's projects. So that's the story phase. The code iterations and test phase starts in January with 20 people, full-time equivalent, 16 engineers, 3 testers, and 1 tech writer, going for 3 months until they kick it up to 26 people for another 3.5 months before they go live in mid-July. And now we're capturing the timeline and the amount of effort expended by their team of 20 to 26 people to build the backlog of 83 user stories that's written in on the lower right, which translates to their count of 252 story points using their scale, which also was manifested in the amount of Java, JavaScript, and HTML that was produced to deliver those 252 story points and 83 user stories in that time window. And finally, the fourth metric we wanted to create and identify is if we understand how much functionality is in the user story and story point backlog, we also want to understand the defect density of how many bugs were in the code representing those stories. Now, it initially says over there under regression testing in June and July that there were about 200 plus or minus defects. And that was their first swag until they got to their Rayleigh curve from their Excel spreadsheets of how many bugs they had found and fixed, and they narrowed it down to, excluding duplicates and non-bugs, 121. So now we have 4 essential metrics: the start, the end date, so we have the duration, we have the head count and the effort, we have the size and the defects. Now, I'll pause here for a minute and say that when you come to our PSQT conference in August, my tutorial on how to capture and use Agile metrics will be using Follett software as a case study, and we'll be actually building files and showing you how to use this data on the during the Tuesday tutorial. And then on the Wednesday keynote, we'll be talking about where Follett is today in 2016. So hold that thought, because another thing that we're going to give you at the end of this webinar is a PDF, if you would like to download it, that goes into details of the techniques used on capturing the Agile metrics at not only Follett, which did XP, but another company, BMC Software, which went with SCRUM. And that document is called How Agile Measures Up at What It Means to You. So jot that down, and if you'd like a copy of that, you'll be able to contact Eric and get the download. Okay, back to this diagram. We drop it into our SLIM database. We save the file. We keep the record, and it's there forever. And we do this 2, 4, 6, 8, 10, 12, 20, 30, 40, 50, 60 times. But for this initial data sample, I'll show you what we found with the first 6 releases built with XP in this environment. So this is a trend line. It is a trend line of defects found during regression test. So the vertical axis is the number of defects, and the horizontal axis is small projects on the left, medium in the middle, and larger on the right in terms of the delivered backlog. The release 5.0, which was about 83 user stories, 250 story points, and about 210,000 lines of new and modified code, is release 5.0. It's the smallest on the left. The other projects in the middle and larger are increasingly larger backlog projects going all the way up to release 8.0. So we have an XY graph. If you remember your good old, grammar school math, we can plot the XY coordinates for a data set of 6 projects. The center black line there is a regression line. That's the comparison from the QSM SLIM database for defects during regression test for pure projects that also were building business IT applications that Follett wanted to compare to. So now when we say, if this project had 121 bugs in this amount of code, how does that compare against the industry average? Is it fewer, or is that number larger? And if you're below that black line, you're fewer. Specifically, if we look at where that black line is on the vertical, axis of that, it's about 50% fewer. So instead of 121 bugs, projects in the QSM database on average show about 240 bugs. So Follett would say for the release 5.0, we're at double the quality. We have half the number of bugs compared to the industry average for a project of that size. And then it repeats consistently on the second, third, fourth, fifth, sixth project. So when we draw a regression line through the red data points and we compare the distance between the lines, we find that on the left, in the worst case scenario, Follett's quality is twice as good, half the number of bugs in the code, and on the right, 66% fewer defects, maybe 2.5 times better than industry averages from their Agile methodology. So now we would say, hey, does this work from a standpoint of clean code? Sure. Not only is it showing us the data, we're actually having a factual number where we can say definitively by how much. And I'll mention that there's a statistics professor at Yale University named Edward Tufte, and Professor Tufte says the essence of quantitative thinking is to answer the question, compared to what? So do we have fewer defects? Sure. Compared to what? Compared to one of the world's largest databases of projects, 12,000 plus, collected by an independent research firm, QSM. So that's the quality dimension. What about the schedule dimension? So if release 5.0 finished in 6 months, how long is that? Is it faster or is it slower compared to industry? And you can see from this chart where now the vertical axis is time, excuse me, we're finding that all 6 projects are dramatically faster than industry. And the curve fit on that shows that it's typically about half for the build and test phase. So now we string 2 statements together. Our style of building code here in our pair programming co-located environment is twice as fast, and we have twice the quality with the same number of people that would be typical of the headcount in industry. And so here's a summary that I was asked to produce one chart. They said, if you met with our CEO, which you will, and tell us, how do we compare? How can you say that in one slide? So I said, okay, now that's an interesting trick. So I came up with this slide, and I said, for the average of the 6 projects, the size of the backlog, what does it show in the Kelly Blue Book of the QSM SLIM Database of the project cost to schedule, the number of bugs in QA, for and the number of staffing for that average size of 6 projects? And then the second column is what's Follett's performance. So here it was, and I said to the senior leadership, you're building a project on average at $2.2 million where the industry takes $3.5 million. So you're $1.3 million cheaper. And you're almost 5 months faster even when we fold in the story phase. So less than 8 months time to market, whereas if you were doing it just average, it would take you more than a year. And when you deliver that system, you've got half the bugs that were exhibited in test, 50% fewer bugs found and fixed in QA. Now some would argue that because the code is so clean going into QA, therefore that's also why they don't have to spend a lot of time and effort in testing. So one of the things that Jim Highsmith, who is the director of our Agile practice at Cutter Consortium, said, in a waterfall world, we try to build the code as fast as we can by throwing a ton of people on it and then scramble like hell to test and get the bugs out. And so we aim for schedule and pray for quality. But in the Agile world, what we're doing is we're shooting for quality first with environments like pair programming and co-located teams, and then we're getting the schedule because we're building clean code. And it makes our test job easier. So think about that. Talk about a game-changing idea of turning it upside down on its head. And that's what we're talking about when we're quantifying this using the QSM SLIM approach. Let me show you a few things about why we see this happening. Well, first, short feedback loops. You're talking about accelerating and shrinking, shortening the distance between feedback loops to get answers quickly. So paired programmers have instant code reviews. They accelerate their mutual learning with face-to-face communication. That's one item. Another attribute is time boxing. By specifically saying we're going to focus on what we can do in the next 2 weeks in this sprint, planning on it in the beginning, daily stand-ups along the way, and a retrospective at the end of that 2 weeks, we're really focusing on clear and discernible progress and getting that nailed down without the attention deficit disorder of trying to focus on everything all at once. We're focusing on one bit at a time, and from that creating an efficient process of going from stage to stage. Avoiding burnout. So if we really believe that a rested mind is a creative mind in this world of knowledge work, then a sustainable pace is important. That's a principle of XP. 40-hour work weeks also makes for happier families, which makes for better morale, which makes for people who really want to work when they're working, as opposed to being pissed off and resentful and exhausted. Transparency. With everything out in the open, secrets don't come back and bite you. Political maneuvering takes a back seat. because everything is out in the open, and things don't wind up cooking and getting stuffed under the table only to emerge later on. So I like this quote by Ken Schwaber. And the metrics provide that transparency as well. High bandwidth communication. We're talking about knowledge work, and we're talking about wide open pipes as domain knowledge moves quickly among the team. And in particular, when we're talking about, say, a pair programming team, we're also talking about rapid mentoring of lesser experienced people by people who have more experience. So I can't tell you how valuable it is to me when I'm piloting a Piper aircraft or a Cessna aircraft and I've got a highly experienced co-pilot with me or a pilot. I mean, talk about accelerated learning. That's one of the things that I find really valuable. One of the people who I enjoy flying with most is a best buddy of mine, Captain Ken Krensos, retired from United Airlines, and he's got 35,000 flight hours in his career as a pilot, traveling between here and Europe and bringing passengers on a Boeing 767 to Zurich and London and Paris and things like that. I love flying with Ken. I learn an incredible amount. And I hope that the younger pilots learn from me when I take them up. Avoiding waste and costly rework. I mean, rework takes time, has cost, creates bugs. Rework is bad. And I think sometimes when we kind of say, oh, we're refactoring, and that's why it took so long, I think it could be a cover-up for the fact that we didn't get it right in the first place. So we ought to think about that. But we're trying to avoid waste and costly rework, and that allows us to finish sooner and have fewer bugs. All of this is actually a manifestation of a rather brilliant mathematician named Norbert Wiener, who at age 14 enrolled in my alma mater, Tufts University, and was a mathematical genius before he wound up teaching at MIT. And he's the father of something called cybernetics, which gave rise to something called Shannon's information theory. So if you felt like you wanted to Google this, type in cybernetics or Norbert Wiener, you're going to find a concept called the feedback principle. It's a key feature of life, from simplest plants to most complex animals, which change their reactions in response to their environment. So the feedback principle is what, say for example, runs your thermostat in your house. The feedback principle is what you use when you click your cruise control on in your car. The feedback principle is what makes a Tesla or a Google self-driving automobile. And the feedback principle is what we're talking about in terms of rapid feedback in creating defect-free code in an Agile environment. So interestingly, it's really channeling and playing right up on one of the most fundamental principles in modern research. Let's talk about the contrary. What about the other end of the spectrum? What about instead of the most experienced people co-located in one place working on one thing with the best tools, what if we have a scenario of this particular whiteboard sketch, which is a project that was offshored in a more waterfall style, where there was a concept phase on the left, a requirements analysis phase, and as soon as all the requirements done, they hand it over to this giant team building up to 95 people in some faraway place. What would that look like? And so let's take a quick trendline look at this case study, which represents the contrast other end of the spectrum. So we drop this into the SLIM database and take a look at how it plots up against some trends. Now this, I'll say, is not a completed project, but it was a plan. It was a planned target, and for illustrative purposes, I'm going to ask you and invite you, what do you think the defects would look like on this project that hadn't started yet, but it's planned? And what did the metrics on this plan suggest as a forecast about what you think would happen from a quality perspective? We'll use this as a little lesson plan. So this is a recreation of this giant waterfall, throwing a large number of people on a project and trying to compress the schedule in the SLIM model. It's release 9.5. It happens to be in the field of electronic medical records in the hospital IT field. And we plotted this project against history of this company. So the history of this company is represented on past projects shown in a trend of the blue dots for the hospital systems division and the brown dots, which was the physicians management systems division. And we cut a trend line through their data in this case. Instead of it being the QSM data, it's this particular company's data. And this is a chart of the schedules that were represented and shown from a data sample of about 24 projects in blue and brown. 3 projects, one of which was what I just showed you, release 9.5, are shown in a red square. We also plotted the planned schedule against this trend for a previous release and a later release. So 3 red dots that hadn't started yet thrown up against this trend of this company's history. What would you say? Well, I can't hear you, but I'll try to read your thoughts. I would say, well, for the Release 9.0 project, that project is positioned roughly in the constellation of our recent past, and while it's faster than the average of our past projects, it's still within the constellation cluster. So it doesn't seem like that schedule for that 9.0 release for the left red square is out of whack. But boy, as we get to the right, with increasing amounts of functionality in the backlog, Release 9.5 is trying to build a huge amount of functionality, even faster than we've ever seen, and the release, actually that should be Release 10.0, not 1.0. That's way also outside of the corridor. So I might say, well, Release 9.5 and Release 10 are way off the chart. We might even say that it's unprecedented. It's in a zone that we might call the impossible zone. So hold that thought. They're obviously shooting for the moon in terms of schedule. And how are they doing it in terms of how they're staffing? Let's look at the staffing chart. Wow, okay, so this is now a chart of this company's past projects with headcount, and the 3 red dots are way off the chart. They're way higher. So clearly now we string 2 statements together. We're trying to build this really fast with a huge team. All right? Now let's put our analyst hat on and say, if you try to compress schedule by throwing a huge number of people on a project, do you think bugs tend to go down or do they tend to go up? Simply as an attribute of a huge team trying to build stuff faster. If you're like most people, you'd say, wow, there's no doubt that bugs won't go down. They're probably going to go up. And then I'd say to you, okay, by how much? From the research data, if we double headcount and build something with 100 people instead of what should be a team size of 50, do you think defects double? And if you thought about that for a while, you'd say, well, maybe they'd more than double. And the correct answer would be they'd double. Because our research shows that defects go up by the square of the difference in team size. So if you double your headcount, defects typically climb by a factor of 4, not 2. So then if I look at a potential trend for defects, where this is the number of defects we've found on past projects, what might we expect for the red squares when they do light up after the fact? Would they be on the upper end of the trend or the lower? Well, you'd say they'd probably be on the upper. And so now we're talking about defect forecasting, heuristically in this case. We could do it far more precise with a model, but you better watch out. If you're going to take the strategy of throwing double the head count on a waterfall type project to try to compress schedule, you better think about the number of testers that you're going to need on this project so that you can finish the testing to get the bugs out and make the date. And so this is where we start getting into mathematical modeling, leveraging metrics, and we'll be doing some of this in the tutorial in August at the PSQT conference. by talking about how we leverage our past to get some sense of what's going to happen in the future. And that's what we call software lifecycle management. So what's your recent past? What's your patterns? How can you leverage that patterns from a historical perspective and then generate an estimate, get a reliable estimate, anticipate the future based on your past, and then while you're in the middle of a project, what would it look like if you tracked it in flight from a standpoint of time and quality? So this is a Rayleigh defect curve for what you would expect industry average-wise in the red dots with a green band and a yellow. However, if you take the idea that this company's strategy would probably show more defects, the blue dots confirm that worst fear. The actuals, which were in blue, spiked way up, more than 4 times in this case. And when we scaled that curve to do a fit, we found that this was likely going to be the forecast in-flight curve that would manifest. Now, it would zig and zag a lot because of test cycles, but overall, when you do a smooth mathematical curve, it's going to follow that red chart, which we did using the computer model. And we could also predict, based on the defects that we're seeing, what date would we hit. In this case, like a GPS, we found that the project predicted a date of November 19th in this example, and it was accurate to within 1 week. Excuse me. So 4 or 5, 6 months ahead of the fact, we did forecast modeling, and we found that we were accurately able to predict a 4-month lag because of the defect curve to within 1 week of schedule accuracy. And so this is kind of the power of metrics that we have when we start to look at patterns. And that's the moral of the story from this contrasting case study. So in this case, using that same comparison, let's say we looked at the Follett data set and what was the industry average. What would an offshore provider average be? So instead of 3.5 million, a little less, 3.2 million when you factor the labor rates. Schedule instead of 12.5 months, yeah, a little bit faster. Not 5 months faster, but about 3 months faster. But the defects we find from dislocated teams with people who have less domain knowledge than the origin company, about 3 times more defects from this data set. Why? Well, these teams tended to use 50 people instead of 35 because let's say that maybe they believe staffing is abundant and they're getting more billable hours if they ramp up to 50 people and they charge the customer for 50 instead of 35. That's why the cost isn't really that much better, because we're increasing the head count. So going back to Follett, if Follett said, should we outsource or should we keep it in-house? This is their in-house. It would cost them more if they farmed it out, because their XP is actually 2.2 million in costs for an average project instead of 3.2 million. So it cost them $1 million more if they farmed it out. So keep it in-house was what the executive leadership did. And if you come to the keynote talk out in San Diego in August, I'm going to tell you what we found 10 years later. Okay, so let's wrap this up and then open it up to questions. We're finding that a Nobel Prize winning economist named Robert Lucas could sum this up by saying that we're getting incredible productivity and economic gains by the force of concentration or clustering of human creativity and talent. So what kind of practical advice would I give if I were to say, what does this case study tell us? First, the source of our troubles, as we saw in the contrary scenario, is the deadline can kill us. We have to be very mindful about whether the deadline that we're shooting for has a backlog that's too big. Are we using a staff that's too huge in order to make a deadline date? So we're going to say that we should learn our lesson and watch when we shoot for the impossible zone. Sometimes going a little slower can actually make you faster. So in the Follett case, instead of taking the temptation of throwing a huge number of people on it, actually said, let's take a little bit more time, and by that definition, they actually wound up going faster just from that practice, because they worked the backlog of being a manageable backlog inside their deadline by proper release planning. So this is a little picture of what's called the 15 puzzle, and as you know, the key to solving the puzzle is you got to get the tiles in order, 1, 2, 3, 4 across the top, alternating white and red rows. But what's the key to being able to solve this puzzle? There's an empty space. So in terms of what you commit in a backlog, don't fill the cup to the brim. Leave an empty space. Give yourself some maneuvering ability. And that'll give you more agility in moving the feature functionality around from sprint to sprint so that you can get things done and have a little breathing room. Finally, use small A teams. Large teams, like we said, double headcount, you get 4 times the bugs. Using a smaller team of highly knowledgeable, skilled people, you'll get cleaner code and you'll make your date. That was the moral of the story of when you read Steve Jobs' biography by Walter Isaacson of the team that built the Mac OS architecture. Small team, smartest people Apple could find in a nondescript building next to a Texaco gas station, didn't even have an Apple sign on it, and they affectionately referred to it as the Texaco Towers. Give them the best tools. The best tools, the best debuggers, the best automated test suites pay themselves back in gold. Because if you can leverage technology, you're going to minimize the manual labor of testing. So as a wrap, whether you're building code that, say, flies a nuclear submarine under the sea to keep the world safe, or you're building code for saving lives in a medical lab, or if you're building code to try to deal with an increasingly overpopulated planet that's consuming a huge amount of resources and maybe driving nature to its limit, or if you're trying to get off of fossil fuel and create renewable energy using the most modern technology with wind or solar. This is my son's former school in Putney, Vermont, the Putney School. Net zero buildings that actually generate electricity instead of using oil, the sun, for their organic farm. Or if you're educating the next generation and igniting the flames of passion, build the best software you can. Because I think some people get it right when they said that today we are building the global digital nervous system for the planet. We're interconnecting people in a more rapid way than we've ever imagined before. And so perhaps we're creating a collective intelligence from all of our technology that can solve the world's problems. As a wrap, I'm going to say that we now have Agile trend lines in the QSM database where we can plot a whole batch of Agile projects, take the dots off, have trends for schedule, effort, staffing, and bugs, and then answer the question when we're benchmarking with our SLIM metrics trend lines and database, what about you? So if you're curious about what your defect patterns might look like, come to our tutorial workshop at the PSQT conference in San Diego, and I'll teach you how to find out what about you, how would you position. One of the features that we're going to offer to attendees is a complimentary mini benchmark of projects confidentially as well of how you might look up against the QSM SLIM reference trends. Whether you're waterfall or Agile, you can take us up on this offer. And better know thyself. So that draws our formal material to a conclusion. We have a few minutes for questions as we wrap here, and I'm going to turn it over back to Eric for the next 6-7 minutes. And comments, thoughts, questions.
Thank you, Michael. While we're waiting for some questions to be submitted. Can you just give me one or two examples of some of your more common questions that you get when giving this presentation?
Yeah, sure. Happy to. One of them is about the Rayleigh defect curve and people saying, what about complexity? That's usually the first question that comes in. And it's directly related to the defect curve. So projects of higher complexity innately will have Rayleigh defect curves that might be taller in magnitude and longer in schedule because it's harder to build that stuff, and we may not always get it right when we're building tough stuff. Projects of lesser complexity might have inherently different and shrunken Rayleigh defect curves. So the question is, what does your environment and the kind of complexity of what you build reveal itself? That's why the QSM database is quite useful, because we can make apples-to-apples comparison by cutting the database to peer development organizations in your industry. So we wouldn't compare, say, real-time embedded satellite development against, banking and insurance applications. We'd compare the banking and financial stuff to banking and financial. We compare aerospace or satellite stuff to the aerospace and satellite stuff. So that's one common question. And then other things that would drive the defect curve, which we're trying to shrink with an Agile environment and a really well thought out test strategy, has to do with some primary factors. Like I said, you can sum it up by saying, to build the cleanest code, get the smartest people you can get, put them all in one place, have them work on one thing, give them the best tools. To the extent that you diverge from those four attributes, you would see your defect curve shrink or expand. And so that's where your Agile also is intended to take that on. And if you're looking at creating an Agile environment, keep those four things in mind. If you start off on the right foot, your defect curves innately will probably be on the better side of the railroad tracks. So thanks very much for asking, what's among the top questions and comments.
Wonderful. Well, thank you, Michael. Looks like that's all the questions that we have for today. So I want to thank you for your time today, and I want to thank everyone for joining us for today's free webinar sponsored by IIST, the Leaders in Educational Base Training. For more information on how IIST can help you or your organization, please visit www.iist.org. You can follow IIST on Facebook, Twitter, LinkedIn, and YouTube to find out more information about IIST news, events, and promotions. If you do want a copy of the PDF document that Michael mentioned earlier in the webinar, please email Eric, E-R-I-C, at testinginstitute.com, and I will make sure to get a copy of that out to you right away. Again, thank you all for your time today. Thank you, Michael, and we look forward to seeing you in San Diego.
Okay, see you in San Diego in August. Thank you, everyone.
Thanks, Michael.